Hey, this is Joel Duff. A few years back, I drug my family to this particular spot. Yeah, like right where my head is. I stood right here with my family standing behind me, begging me not to get any closer to the edge, and took this panoramic photo of the goosenecks of the San Juan River in Utah. Why did I drag them there? Well, for one thing, I think it's just a spectacular geological site. Right? Just like if you're close, and we were in Mexican Hat, we were going to drive up to Moab from here, and we had just visited the Mesa Verde area. And so it's like, this isn't too far off the way. You got to go. I mean, you have to go. I mean, hopefully it's below 99 degrees when you're there, but no guarantees of that. It's a barren place. And you drive across a fairly flat plain that's a fairly nondescript desert. And suddenly you get to this point, and there's a small state park here, and you walk out to the edge and you get this view. All right, you get this magnificent view. And this view to me is incredible, and it says something in one picture that's really profound. I think you can't stand here. It's kind of like standing at the edge of the Grand Canyon. There's many other places where you can stand, and you're kind of faced with the immensity of the geological column, right? And the grand diversity of that geological column. And really you're faced with the question of, how did it get this way? How did you get this meandering river right here that has cut itself down 1,000 feet down into the bedrock? How was this particular scene created? And more importantly, how long did it take to paint this scene? Let me tell you about two different models for how this canyon was formed. The first is young Earth creationists. Now, had I visited this location with a young Earth creationist, and they were standing next to me and they were looking out in awe at this particular, I mean, nobody cannot look at this particular picture without awe, right? And I were to turn to them and ask them, well, how would you explain this? How would you explain what we're seeing? They would doubtless paint some kind of dramatic picture of a catastrophic formation, a nearly instantaneous formation of this particular scene, right? According to their model, about 4,500 years ago. And after Noah's flood had receded, this entire region was a vast plain of freshly deposited sedimentary rock. Then suddenly an enormous lake, all right, it had covered an area larger than some states, burst forth from its natural dam, being held back by some loose sediment from the end of the flood. And this area, or just north of it, this huge area of water suddenly burst through this dam. They would say that the rushing waters then carved all these dramatic meandering canyons in just a matter of days, possibly a couple weeks, as all the water drained from the Colorado Plateau. Now, I think, though, as we gaze down into these spectacular loops in the river below, where the San Juan River has carved out, as I said before, this 1,000 feet of ancient sandstone layers, I think we have to ask, could such intricate patterns really have formed through a single catastrophic flood event? Is that a very realistic scenario? And my answer, of course, is no. This makes no sense at all. To me, this place, this particular spot, looking out over these goosenecks, this meandering river, is amazing evidence of a long, slow process occurring over hundreds of thousands of years. So let's talk about that a little bit. I want to show you a few other pictures that I've taken and give you a better sense for meandering rivers and how this incision could have taken place. So I was inspired to make this short, what will hopefully be a short video on meandering rivers being incised into canyons and how it is an amazing testimony to an ancient Earth and just completely defies the young Earth creationist flood geology model. But this picture is what, got me re-inspired. I had already known about the San Juan River. It's this picture that hit me when I was scrolling through Facebook, because it shows the San Juan River coming in, taking this sharp bend around here, coming all the way around, nearly coming back and connecting with itself before going out through this canyon. The idea that all this area was a basin and at one time had a horizontal surface, and that somehow water rushing across it in the matter of a few days carved this kind of canyon just makes absolutely no sense to me. It doesn't just make no sense to me. It doesn't make any sense to physicists and chemists, right? And geologists. Anyone understands the way water and erosion works, the way water flows, fluid dynamics, all these different fields that come together to try to understand erosion. None of them would predict the thing that I explained about what young Earth creationists would, their argument for how these formations were made. So here's the, again, this is just a small segment of the San Juan River in southern Utah. And now you're looking straight down upon it. And so you're seeing this green line is the river itself. And then these are the canyon walls sloping up. And then the relatively flat surface, all right, of what was originally this high plain. And this is the Goosenecks of the San Juan right here. All right, so you see this road coming down here. And where that first picture was, where I took the picture, was on this point right here, this little tiny point right here. There's a little parking lot right here. Again, you have to drive, 15, 20 miles through the middle of literally nowhere. And you don't think you're seeing anything until you get to this very point, and all of a sudden, this amazing vista is a feast to the eyes. But you see how close this river comes. And then eventually it goes here, and it's going to bend around in some crazy shapes, which I'll show you in just a moment. There is an area here where there's, I think it was 1.5 kilometers as the crow flies. The river has to go 6 kilometers in order to get to that same position. That's how twisted this path is. There's no obstructions. If you let water flow across this flat surface originally, there isn't any obstructions like telling it needs to move in a particular direction. It'd be a flat plane. And yes, you can get meandering streams on a flat plane, right? On a big river plane, right? That's, relatively the same height everywhere. That's why you get these rivers that move and curve back and forth, and they move positions over time. But if you have a massive flood, you don't get this, right? The speed of the water it prevents it from being able to produce these particular types of sharp bends. So here we are back at the Goosenecks, and I'm just that's Shiprock, by the way off in the distance, a famous volcanic neck that's protruding through all this other sedimentary rock. So that's a whole nother question, right? You have to have a flood lay down all the layers, and then you have to have an intrusion of magma up through there to form a volcano. And then you had to have erosion of the volcanic material, leaving just the stem of the volcano. But again, you can see kind of this amazingly flat surface at the top. And so here comes the river around the bend, and there's so many different layers. And many of the layers have different densities, all right, different hardness to them. And you know that because there are cliffs, right? There are fairly sharp cliffs, and then there's areas that are more brittle and erode more easily. And that's a testimony to different conditions under which each one of those different layers was laid down. All right, it's thought that this is a big basin between two large mountain ranges at one time. So there's erosion happening coming into a large lake in that basin, and then sediment falling out. And depending on the type of sediment and the amount of sediment being put in, you get different densities of that sediment. So you get claystone, you get sandstone, siltstone, right? And those then, when they harden, have these different properties of different erosive properties. So not far away from the Goosenecks, right? About another 30-minute drive. You drive back across the plain. Then you go up, I really should have put a picture in here, of an amazing road, a switchback road that's unpaved, to get to the next level, the higher plane, all right? And up there, actually you can see way off in the distance some Monument Valley portions of the Monument Valley. And if you think about them sticking up, essentially I'm on the very top of those mountains. And so this entire segment of rock also would have expanded all the way across, right? So everything had to have been eroded down and then created a flat plain. And then you had more erosion with this river in there. So I'm standing on a precipice here. Again, I forced my family to take a picture. We took a big selfie there, set up my tripod and everything. Got this great shot of my family, except I'm missing one kid because they refused to get out of the rock. Uh, yeah. So there, and this is looking a different direction from that same location. So when I was looking basically east, and then I kind of turn, I'm looking more westward here. And so here we see this higher level, right? And then we see this large plain out here covering this vast area. And then what's etched into that plain is this just incredible, I just keep saying, because I'm amazed by it, right? I'm just remembering actually being there and how incredible this scene is. So what are these things? These things are called entrenched meanders, right? I mean, you see modern rivers on a river plain, as I mentioned before, that meander, right? And the meanders move through time. They move locations. Usually what happens is there's a flood, and the flood kind of pushes it, forces it through, it cuts through, and it creates a new meander. And then it kind of settles into place there, and it might stay there for a while. And then another flood kind of pushes it out of that meander, and it creates another one. All right, what an entrenched meander is if you have a stream and it's going across a large flat valley, and it stays in that position long enough. In other words, it's about the same amount of water consistently, and it's already built sort of a little bit of a trench there, right? It's eroding. Then once it's in place and it can't flood and get out of the trench that it's in, all right, it's going to stay there. And then as it does so, it's going to continue to cut down. Now, why would it continue to cut down? There's only really two ways that can happen, right? It has to be going downhill pretty well towards some location and carrying the sediment away. In this case, what's happening is this whole area is being lifted up. This whole area actually is higher than on either side. All right. The river comes in, and actually the elevation kind of goes up, and then the elevation goes down eventually across. I mean, I'm speaking very generally here, but there's a hump right here, and the river just like goes right through it. And again, if you say if there was a large lake and it wanted to get across this area, it's not going to go up and then over, right? It would go around. Water's going to find, the easiest way to get to that lower elevation. So how did you end up with a deep canyon running through, in some cases, ridges, right? There's ridges, and it goes right through the ridge. Because it was all flat at one time with a meandering river, and as the rocks were lifted up and gradually bowed up, all right, as mountains formed and other things are happening, you're basically pushing very slowly, just half an inch or less, per year, it's moving up. But if there's already a river there, as it moves up, it continues to cut down, right? The water just continues to cut through that rock and carry away the sediment, and it just keeps going up, 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 and the river just keeps going down, down, down. Actually, it's not actually gone down very much at all. The river's probably about where it was originally. It's just that the rocks have gone up, and that's what's allowed it to eat through those rocks in this way. Now, the way I'm describing that, what does that sound like? It sounds like a whole lot of time. Yes, we're talking about how that happens is just this whole area is rising, and the river has to cut it. And we got 1,000 feet to go through. So that's going to be a lot of time of erosion. The other thing is the meander, right? And that's kind of my main point. You don't maintain a meander, all right, in a giant cataclysmic flood. All right. But once the meander's there and it's cut, and you slowly allow it to continue to stay in that same position, and you simply raise the land, it's going to cut right down wherever the meanders were. And so you had this huge loop out in a large flat plain. You had a huge loop because there was a big river there, and it's just kind of meandering across, right? There's no particular direction it needs to go other than maybe just a slightest slope across 50 miles. And so it just meanders out there. But then as you start to lift the land, it starts to cut down, and then it's stuck. It's stuck in the meander. And from there, it cuts. Now, young earth creationists might say, maybe this river was here out in a flat valley, and it was starting to cut in a little bit. And then the floodwaters let loose, and then they came through, and they went through the meander, and they quickly cut down. Not going to work. Not going to work. It really isn't. For one thing, you have to say that this is rock. It's not going to cut that quickly. It's not going to cut in a matter of a couple days. And the other thing is massive amounts of water are going to have a different erosional pattern than what you're going to see here. Obviously, this isn't the only place where we had these meanders. But all of these meanders in the San Juan Valley and the San Juan River, and then in the Colorado River, what about Horseshoe Bend? Horseshoe Bend's just north of the Grand Canyon. That's a very famous sharp bend with that fairly large river, and it's a sheer drop there. I mean, this is not as this isn't as steep at the Goosenecks. So that's an incredible canyon that is formed, and you can do the calculations. That's what I'm asking young earth creationists to do, right? They throw out this really vague, like, well, how did that form? Oh, lots of water over a very short period of time, just really quickly eroded it. I looked up a couple papers about meanders. There's all kinds of papers that look at the fluid dynamics, the amount of water, the amount of erosion that occurs, and the pressure from the flow, right? How much flow do you have to have in order to erode off the sides and make the meander stretch out, right? Versus if you have a constant low amount of water, it doesn't really put pressure on the sides on either side, right? So it's just entrenching. It's going down as the land is lifting up. And so they can tell by looking at different rivers what kind of volume of water they've experienced in the past, depending on where the erosion is on which side of these valleys where it makes turns. The signs of having massive water flows are limited to non-existent for most of these meandering rivers in the Southwest U.S. And then, of course, you get down to the Grand Canyon. This is my picture of the north end of the Grand Canyon, not on the north side, but I should say the east end of the Grand Canyon, the east point you come in. And of course, the Grand Canyon is a massive amount of erosion. And what is the explanation for the Grand Canyon, according to young earth creationists? This was all laid down sediment by global flood. And then later, after the flood, after some undetermined amount of time, this huge flood, which apparently started even north of that the San Juan River area, yes. A huge flood from a lake suddenly bursting forth just flowed over here and created the Grand Canyon. Now, the Grand Canyon's a little more chaotic looking. It doesn't have that clean, incised meander, although the Grand Canyon actually has quite a bit of bend in it too. More bend than you would expect if you had a massive volume of water running through it. All right, so what the Grand Canyon is, again, it's also the result of uplift and the river just cutting down as the land is lifting up. And it's a little bit of water over a long period of time, not a lot of water over a short period of time. The evidence is lacking of the latter. And all the evidence points to the former, that these things were eroded by slow processes occurring over millions of years. Here I am at the Grand Canyon. Been to most of these locations multiple times. And again, the Grand Canyon is awesome, but I like the Goosenecks for just the simplicity of the erosion there, right? The erosion there is just, I got to show it again, right? It's just like, it's so consistent. And that's the amazing thing about these bands of rock is that they are, they go all the way across. I'm sure you could map, this little thin layer of rock here. Actually, that's probably not so thin. We're probably 20 or 30 feet, solid sandstone here. But you could just walk around that particular layer all the way around. You could find it over here. Actually, it's probably right here, and then over here, and then you can go over there. And, for many, 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 many square miles, you have the exact same layer, about the same thickness. That also is a testimony to an ancient Earth. How would you get that same thickness over a large swath of area? That represents a calm sea, right? A calm, shallow sea or a calm, shallow lake, right? Where you have this whole area covered with water. You have a sediment input from various places away from here. You're right, creating sediment in the water, and then it's falling out of the water, and then just very, very, very slowly piling up. And because of the mixing of the entire vast lake here, you end up with about the same amount of sediment across many square miles and the same exact kind of sediment. And then as the climate changes, the type of sediment input changes. More organic matter, less organic matter, finer particles, you know, larger particles because maybe you have higher volume of water coming in, inputting into the lake, right? Each one of those things then represents different time frames, different environmental conditions that allow those different layers to form. A global flood, I don't know how a global flood forms thin layers of the same thing, of the same particle size across many, many, many miles, right? When supposedly it was a catastrophic, violent event that's covering the entire earth and stuff's just sloshing all over. So that's why this picture, this image right here, has multiple different ways of pointing you to this is the product of a lot of time and a lot of different events, none of which occurred very quickly. All right, let's wrap it up with one more thing, because I'm going to go back to the young Earth creationism thing, and I want to show you what I want to show you that they do try to compare the canyon I just showed you to Mount St. Helens and the erosion that occurs there. And I just want to show you how ridiculous that is now that you've looked at the San Juan River Goosenecks Canyon. Okay, so here I am on the Is Genesis History website. Is Genesis History was a young Earth creationist documentary from a few years back, I think maybe 2017. And it prominently portrayed the story of Mount St. Helens as an analog or a comparison to what a global flood could do with respect to erosion. And so the question here is, what actually happened at Mount St. Helens and how does that relate to a global flood? In the film, one of the first places we filmed was Mount St. Helens. I knew from the start I wanted to show people how quickly a landscape could be transformed through catastrophic processes. And this is what I'm sure that if I were standing next to most any young Earth creationist at the edge of the Goosenecks, and I were asking them, how would you explain what we're seeing here? They wouldn't try to explain the things we're actually seeing at that location. I'm pretty sure they would point to Mount St. Helens because that's the example they would know about. They would say, like, look what happened at Mount St. Helens. Whatever happened there, that's what could have also potentially happened here. And that's what the author of this blog is saying, right? Hey, I love to show Mount St. Helens because that shows how catastrophic events could have very quickly shaped our Earth. Yeah, so he says here, well, we got there. So they went on this hike. And what they're hiking to is they're hiking to a particular valley, a valley that was carved by events that happened after Mount St. Helens explosion. It was pretty amazing to see in real life what Steve had been talking about. Just looking around, seeing that what was a very normal landscape and one that hadn't existed 40 years before was eye-opening. How many things I had looked at and had just assumed were very old because that's what I'd been taught, right? Look at this landscape. This landscape didn't exist 40 years ago. And yet here it is. Look at this, it's an amazing canyon. If this could have been formed in less than 40 years, then, hey, if you got 4,000 years, you could do a whole lot of things to reshape the earth in that period of time. I mean, that's the sentiment of this paragraph. So under this section, how do we know how old things are? Goes on to say, this is one of what Steve Austin, he's the one that has studied, the young Earth creationist who has studied the Grand Canyon, Mount St. Helens quite a bit, refers to Mount St. Helens as the Rosetta Stone of catastrophic geology. Right? If you study this spot, it's the Rosetta Stone, meaning it will help you understand all other places on Earth. It links up eyewitness accounts of a major volcanic eruption and decades-long aftermath with the observations of forensic data. Hey, we've been collecting data here. We actually saw what happened. We have video evidence of what happened, and we can connect that to like the changes that have occurred. And therefore we can use that to try to understand other formations that we see in other places, apply that knowledge. Sure, I agree. But not every other place on Earth is an exact analog of what happened here at Mount St. Helens. What it demonstrates in his mind is that it doesn't take nearly as long to create certain geological features or structures that had been previously assumed. Then he goes on to talk about these 4 things that, like, you should say to somebody who's not a young Earth creationist to convince them that maybe they haven't really understood geological processes as they should. right? What happened here? Well, we've got rapid sedimentation. It's strange to think you're walking on part of the earth that simply didn't exist when you were born, right? We got to the bottom, we saw many different layers, including thin laminations and that of flat boundaries. It was obvious that a lot of things had happened in a very short period of time. Rapid erosion, right? Yeah, we know that all eroded in a few days. There was a burst lake that then caused water to rush down through this area. Well, here's the area. And this area was full of volcanic ash. Where'd the volcanic ash come? Well, Mount St. Helens, right? Huge explosion, very effusive, lots of ash thrown up in the air. I mean, the mountain slumped, but then you had lots of ash thrown up in the air. That ash is falling out, and there's multiple days of events where it's going on, and it's stacking up layer by layer by layer. Why are there thin lamina, which are just like really thin layers of sediments? Not rock, by the way. This isn't rock. Thin layers of ash. There's thin layers because you had, puff of ash flies up, right? Gradually settles down into a little thin layer that covers this particular area. Another, maybe a half inch, and then there's like a millimeter, and then there's something else, right? Every couple of hours, every couple of days, there's a couple more layers, right? So you are stacking up layers, and there's different properties to that ash depending on, the volcanic, the magma, and how explosive it was and so forth, right? It changes some of the characteristics of that ash. So that's why you can see different layers. Partly why you can see different layers. Right, so then you had all this ash laid out in these really thick beds. So you're talking 30, 50 feet of ash. There's actually a little bit more in a couple other places. And then you have water run through here. And guess what the water did? Well, this is soft ash, right? It just eroded right through it and created this valley, like virtually overnight. And so if this could happen here, I'm not, I'm trying to be nice, but this is what people would say standing at the Grand Canyon. Well, look, they have that canyon up in Mount St. Helens, and that was created overnight through all, 30 or 50 feet. So what if you had like a couple weeks or a couple months of water draining out of the western US through this area? It could have made the Grand Canyon. Grand Canyon isn't made of freshly laying down ash that's not rock yet. And by the way, if you think about if you want to say, well, it was all turned to rock right away after the flood, and so then it was carving the rock. Well, then you have the problem of like, how long would it take to carve rock? That's going to be much harder. But if it wasn't rock and it was still soft sediment, I mean, look at Horseshoe Bend, look at the Goosenecks. That's really steep, right? There are sheer cliffs of sandstone, and then there are siltstones and other some softer rocks, right? Shales. And then there's more sandstone and more shales and more sandstone, shales, sandstone, shales, and so forth, right? All the different layers. And it's very steep. If those had just been laid down by a giant flood, well, for one thing, they'd be still full of water, right? They wouldn't been dewatered yet, so they wouldn't even had a chance to lithify and turn into rock, and they'd be soft. And if you cut down through that fast through the soft stuff, what would happen? It would all have slumped, right? So you couldn't make that from soft material. So it had to have been hard, right? Also, if it was fairly soft, it also would have just cut straight through it in a straight line. Oh, maybe like Mount St. Helens. It's like, I don't see any meanders here, right? This is just like cut right through. Took the path of least resistance and just went straight through here and cut a straight canyon. Yeah, so we need a paradigm shift. Mount St. Helens allows us to see how fast things can occur. They can occur quickly. No doubt about it. Not denying that. Under certain conditions. And the material that's being cut through is one of the two main factors that determines the erosion rate. And that is, right, the density and hardness of the material you're cutting, and the amount of cutting material you have, which would be water. So yes, they might want to say, oh, well, there still was plenty of water around to cut. Then you have to deal with what you're cutting. The conventional explanation for the Goosenecks of the San Juan River, for the Colorado River, for Horseshoe Bend, for the Grand Canyon, is consistent water, but not vast amounts of water over long periods of time. And it's completely consistent with everything we see in the geological column. So there you go. I'll call that another episode of Critiquing Creationism. If you haven't gotten the point, I mean, the point is that those geological formations, they don't fit in a young Earth scenario. I have not heard a young Earth hypothesis to explain these geological formations that makes any sense at all. And if they want to, and I know that Andrew Snelling and others just say it as if like, hey, I got a PhD, I'm a geologist, and that's what could have happened. What could have happened. And often they say it that way. That's what could have happened. But you know what? A non-expert that hears that, but they hear it from an expert, they hear the word could, and they don't hear like, well, that's just a super speculative idea that I actually have no support for. They just hear, oh, a PhD geologist said that. Yeah, that means it really could have happened, as if really could have happened is different than just could have happened or may have happened. You see, they're not coming with like support for that hypothesis. They're just stating the hypothesis. And the reason for that is that's all they've got. It really is. That's all they've got. In the comments, point me to some papers by young Earth creationists that actually dig into like the numbers, like modeling, doing some statistics, doing some simulations, because I've seen simulations published for meandering, for incision rates, there's actually, I was going to go to another study, but I'm like, this is going too long already. There's an interesting paper out there that looks at the dating of sediments on different shelves, on different layers of the San Juan River bank, right? And dates those rocks in terms of how long they've been exposed. And that paper looks at basically sands and sandbars, because there's actually, if you go up like 500 feet on some of those shelves, especially around the bends, there are thick layers of 4 or 5 feet sometimes of gravel. And that gravel is not debris that's fallen from the cliffs above. That is gravel that was left there when the river was all the way up there, right? And they can look at how long that gravel has been sitting there by the exposure to light. All right, it's called cosmogenic dating, and it's an interesting form of dating that allows you to get a rough idea of how long those rocks have been exposed to the light, or basically since they were eroded out of wherever they came from. And so you get a rough idea of how old they are. Well, guess what? The sand, the gravel bars that are high up are much, much, much older. Hundreds of thousands of years old. And then as you work your way down, they become younger and younger and younger until you get to the new sandbars at the bottom, which are the youngest. But from dating those, you can get an idea of where the river was at different times. And then you can calculate how long it took for the river to go from up here to 100 feet lower, and then 100 feet lower, and 100 feet lower. And you can estimate then the erosion rate. And not just for the whole thing, which you can do for the whole thing. You can also measure the erosion rate from, every 50 feet. And if you do that, you can find out if the erosion rate changed over time. It turns out the erosion rate was faster in the past, which makes sense because this is a very dry area today, but we know it's wetter in the past, which means there would have been a higher flow through rate in the San Juan River in the past. All right, so the erosion rate you would predict would be faster, and that fits with the data that we've actually found through investigations, right? In other words, you generate a hypothesis, right? We might be able to estimate the erosion rate by looking at dates of these gravel bars. And then one of the other hypothesis is you might predict before you even start. You might say like, I think that we have other evidence that the climate was wetter in the past, especially at the source, the San Juan Mountains. And therefore, we'd expect a higher flow through rate, which means we should see in the data that we collect, we should see a pattern of faster erosion and then slower erosion today. And that's, lo and behold, that's what they found. Now, young Earth creationists, they could not predict that, right? Because they're going to say the entire canyon was formed almost instantaneously. Right? So all the gravel left at every layer is only days different from each other. So it shouldn't even be dated to different dates anyway. It should all date to the same date, even if the type of radiometric dating they're using is bogus. It shouldn't give any pattern at all, but it does reveal a pattern. So that also defies young Earth creationists' predictions. Yep, the longer I sit here, the more ways and the more pieces of data don't fit with the young Earth creationist model. So for their sake, maybe I better just stop right now. Thanks. We'll see you when we see you. Bye-bye.